Hello, class. Okay, so we're going to continue talking about conduction. And I'll do one more problem because this one is a little bit different than what we've been doing before. It's a problem I found in a book, so I'm going to read this problem off. Basically, we have say like two walls here, and there's a pipe, like a metal pipe carrying steam. And we'll say the length of this pipe, we're calling it D. Because we use L in the formula for power. And I don't want to use L for the length of the pipe because in this case, this is a pipe carrying steam. So there's no difference in temperature between one end of the pipe and the next. What we want to look at is the heat flowing through the pipe and entering the room. So the pipe itself is steam at 100 degrees Celsius, and the room is 11 degrees Celsius. And so heat is going to flow from the pipe into the room. And so this is one perspective. I'm going to draw another perspective where, say, here's a cross-section of a pipe, and it has a diameter of, let's see, 5.4 centimeters. And, of course, the steam is 100 degrees. Now, the pipe itself is made out of metal, and we're going to say it's a very thin metal, and the metal itself is also 100 degrees. However, the pipe is surrounded by a layer of insulation that has a thickness of 5.2 centimeters. So that's like a side view of the pipe. And again, energy is going to be flowing out into the room. This is just a cross section. It's going to be coming out, they're all surfaces of the pipe. And we want to find the rate that heat is going to escape. So again, this is a layer of insulation here. So this is hollow pipe, like the pipe itself has some thickness, which is fairly small or fairly thin, so we don't have to worry about that. And the pipe is the same temperature as the steam. So basically, heat is going to flow, we'll just look and say this direction. Now, we have a little bit of a problem with this, applying this formula the way it's written, though. Because let's say we just tried to apply this formula. K, the insulation, well, say we know what that is. I'm not seeing. It's 0.048. Let's write that down somewhere. 0.048 watts per meter Celsius degree. So we've got K. Delta T is fine. We have 100 degrees inside, 11 degrees outside. It looks like L is fine too. We're just going, 5.2 centimeters. The problem is with the cross-section A. Because what is A? The cross-section. If you look here, like we've got heat flowing in all directions. And so if you look at this layer here, just like this, let's look at this first layer here, which has a thin thickness. Let's just say it's a very thin thickness. The cross-section area would be just like the area of this circle here. Or we have basically a cylinder here. So we have a length coming out of the board of 6.2 meters. And, you can picture like a cylinder, just unroll it. And we have essentially a rectangle. And so if we look at near the pipe, we're going to have this area here, this circumference times the length. But if you look at the outer edge, we're going to have a much greater cross-section area that it's passing through. So what we want to do, I'm going to erase this line that I drew. Let's look at a particular surface here. That's at a distance r from the center of the pipe, and let's say it has a thickness dr. And now we can calculate the heat flowing through this, as long as dr is small, it's infinitesimal, we can consider that A in the formula just the length of the pipe times the circumference at this radius. And so we can consider this like a very thin slab, and then the next slab is going to have a greater area. Like each slab, as we move outward, is going to have a greater area. So I want to write this formula in a way that's better suited to this problem. So if we consider a very small, like a very thin, let's just look at a slab of material with a thickness, let's call this thickness dx. And the temperature difference between the two ends is, let's say here we have T, and here we have T plus dt. So heat is flowing this way. Then the power would be Ka dt over dx. Now the book puts a minus sign in there just to get the direction, but I usually don't care about that. So don't worry about the minus sign. We know heat flows from hot to cold. So anyways, let's apply that to this problem now. So remember the area of a cylinder. So if we have a cylinder with a length d, and say, I'm going to make this a bigger cylinder. Again, you can picture unrolling it, like, actually, here's a cylinder. We're going to actually try this. So I'm going to mark a line here, like right at the edge of where the paper is. And if I want to find like the area of this outer surface, you can just unroll it up to this here. And so this length we could just measure directly, but the circumference here, or when we unfold this, then this would be the circumference because we wrap around exactly once. So this distance would be 2 pi r. Like this. This is d, and this one is 2 pi r. So the area here is 2 pi dr. So the area okay. So now let's apply this formula. We're looking at, in this case, dx, that's the direction that heat is flowing. Like if we had that slab, remember dx was the thickness of the slab. And here we had T and T plus dt. So like dx is, like delta T is a difference in temperature here. Dx is the width of this. So again, dx is in the direction that heat is flowing. So in this case, it's going to be, we're going to replace dx with dr. So let's do this. So we have power. I'm going to rewrite this formula for, and again, it's, if we just did this directly, we'd have d times 2 pi r. But r is the variable that's going to be changing, so I put that at the end. And so here, if we write down our formula for power, we have Ka times dt over dr. And if we plug in A, here I'll write it this way, we have 2 pi K times 2 pi capital D times R dt over dr. And we can clean that up a little bit. But what we want to do is let's rewrite this in like differential form. So let's collect all the r's on one side. So we can say P times dr over r is 2 pi kd dt. So just by moving things around, we don't want to really call it multiplying by dr. Mathematicians don't like when you do that. But, we move this over here, we write it in a different form, and then we can integrate. Now, the rate that power flows through should be constant, so we can take that out of the integral. And K and D, and obviously 2 pi, and so if we integrate both sides, this is what we get. Now, we're integrating from the pipe itself, where the temperature is initially 100 degrees, and we're going to end at 11 degrees. Remember I mentioned to neglect the minus sign? In this case, we should actually put this in there. So yeah, let's put the minus sign in there. Because I just realized it's going to give us complete nonsense if we don't do that. So let's put the minus sign. And then the radius, we're going from 5.4 centimeters. And then we have, 5.4 to 5.4 to 10.6. So let's make sure we can see this. Now this integral on the left, the integral on the right is completely trivial. That's just delta t. So let's actually write one more thing. Let's distribute this minus sign. So remember, you can change the limits of integration by multiplying by -1. So we can say from 11 degrees to 100 degrees Celsius. And then that integral is just going to be 89 Celsius degrees. Now on the left side, this integral dr over r, that's the natural logarithm of r. So if we do this, I don't like using this board to work things out. Kind of out of room though. We have P times the natural log of r evaluated. Here we have 5.4 centimeters to 10.6 centimeters. The units actually don't even matter in this case as long as they're the same. That's equal to 2 pi kd I'm just going to call it delta t. The integral of dt is just delta t. So, now, in general, let's just say you have the natural log of x evaluated between a and b. This would be ln b minus ln a, or ln b over a. So we have p times the natural logarithm of that fraction. But we want to get p by itself, so let's divide by this part. So we have 2 pi kd delta t divided by the natural logarithm of 10.6 over 5.4. So that would be the power. And again, we have to write it in this form to do it because that area is changing for, like, we consider this like concentric rings that start at the pipe and just keep growing until we get to the outer edge of the insulation. And each one has a different area. So we have to do this the calculus way. And this dt over dx, that's called the temperature gradient. And and then it's a matter of plugging in the numbers. We might as well do that. So I'm going to have to make room here. Well, we've got everything we need. So let's plug things in. I erased the conductivity, but that's in there. Okay, so power. We have 2 pi. Now K, I'll bring this back here. What was K? I think it was 0.048. Yeah. Now let me take this logarithm. Let's do that first, because that's just a number. So natural logarithm of 10.6 divided by 5.4. This is 0.67. Okay, so that's the 2 pi over the logarithm. And then we have K, which is 0.048. So I'm going to write that as 4.8. And again, that was, so then over 100. And that is watts over meters Celsius degrees. D was 6.2 meters. And delta T was 89 Celsius degrees. So if we look at this, the meters cancel, and we're going to get power in watts. And let's just get this number here. So what I'm getting is around 248 watts. All right. Yeah, so anyway, stop there. And again, sometimes, writing it in this form will be necessary. A lot of times you can just use this simple formula, but occasionally the other form will be necessary.